Okay, finally I'm seeing some parasitic oscillation. See that thickening right there on the top of that trace? That's the A load trace, or rather not exactly the load trace. I'll show you in a minute. Okay, so this is Aaron's circuit. This is my 0.066 ohm non-inductive shunt here that I'm using to view the current. There's the current viewing probe on either side of that shunt, just like always. But I noticed from Aaron's pictures that he's scoping his MOSFET at the drain side of the load rather than at the battery side like Ainsley does. So we'll put the probe, the A probe, right there on the drain of the MOSFET. And I've varied the parameters of the 555. You'll see that I'm using a 1.1 kilo ohm resistor there, and a brand new battery that I just took out of the box, and actually it works on this one too. Okay, anyway, so we have successfully got the dial set to produce a nice parasitic oscillation right there. I'm going to magnify that on the time base so that you can see how pretty it is. It's really neat. See that? And I'm going to amplify the voltage some as well. And crank it back down. Okay. That's a beautiful textbook parasitic oscillation, and you can see that it is made up of a very complex signal in there. And if your scope is trying to trigger on that, it won't trigger. But the oscillation itself is regular. There's nothing irregular about that. It's an oscillation. And you can see the details in there. Okay, and if I really try hard to convince my scope that that's where it needs to be triggering, I don't know if I can. Let's see. This Philips oscilloscope has a really hard to fool triggering circuit. It might be possible to extend. No, all that's just there. Anyway, that's that parasitic oscillation. But look where Aaron is monitoring. He's looking at the load resistor, at least on the video that I saw here. And of course that produces that oscillation. But if I take this and I look at it where Ainsley says to look at it in her diagram, that is there, that oscillation goes away. Everything goes away. There we go. What have I done here? There it is. And there it's not. Oh, it's still there. You can still see some of it, but it's much less magnitude on that. Okay. Now, if I can somehow shorten the duty cycle so that the scope attempts to trigger on that, or so that it gets down into where the triggering is, then the oscilloscope might lose its trigger and go kind of nuts. But like I said, this Philips oscilloscope has a really good trigger circuit. It's hard to fool. But anyway, we have seen the fantastic parasitic oscillation now. And it's still being caused by the 555 timer kicks. There it is there. But at least we are actually seeing something that any engineer would recognize as a true parasitic oscillation up in there. And it shows up much better if you scope right at the MOSFET, which kind of leads me to believe that it might be. Where'd it go? Where'd it go? There. Kind of leads me to believe that it might actually be coming from the leads of the scope rather than the MOSFET. That's classic parasitic oscillation, and you can see that it is regular. It's not chaotic. There's a complicated waveform in there, but if let's see, if you really go, I can't get my scope to want to trigger on that. Just won't do it. Ah, there we go. That's the mains trigger. That doesn't count. Never mind. Okay, I'll bet I could get it to false trigger on this oscilloscope though. Okay, parasitic oscillation confirmed, but if Aaron can't show this kind of a trace, he's not showing a parasitic oscillation. Thanks.